Hello, my name is Ryan Houston and welcome to my Portfolio 4 worked example. Alright, so first things first, I'm just going to redraw the circuit in a simpler manner. So you'll notice I've left out the inductor L because it is defined as 0, or approximately 0, and I've also removed the gearbox from the system as well as adding the armature inertia, which is not drawn in the previous image. Step 1, we want to find an expression for torque with all of the components translated onto the left-hand side of the gearbox. So this is done by using this gear ratio here. So basically you got the components, you got the inertia of the armature, and you got your KL1, which is your spring between JA and JL. So you multiply both sides by N1 on 2 to find Tm by itself, and this cancels out a lot of the expressions nicely on this right hand side, and so you end up with an expression of Tm here. So similarly to step 1, we can now sum all the torques about JL to find an expression for theta L in the complex domain. So this is done by finding the torques about JL. So this JLS squared is the the inertia of L, sorry. Now this DL is the dampener. These KL terms are the corresponding springs, so KL2 being going to ground, and KL1, which is the spring in between JA and JL. So you can simplify that and it gives you this nice equation here in terms of theta M in the complex domain. So step 3 is to sub in the formula for theta L in T of M where theta L occurs, so that we have all our expressions in terms of theta M in the complex domain. So simplifying this mathematically, we can bring in the theta M out the front and simplify this expression in the brackets nicely to end up with this formula here. Step 4, we just want to find a function of EA with respect to torque and angle. So this derivation here was made in tutorial 4. However, you can see the influence the formulas I've provided have on this equation, as well as KCL stating that current at each node must equal 0. So similarly to question 3, we're just going to substitute the formula for T of M wherever T of M occurs in the EA function. So as you can see, this whole expression here has just been rewritten. And so we can take the theta M over to this left hand side to get our first transfer function. However, this will need to be expanded to be theta L in the complex domain over EA in the next step. So as stated in this step, we've substituted in the formula for theta L into the previous equation from question 5. We've also swapped the numerator and denominator around. So quite a lot has just happened here. But this basically just gets us into our final form, in which we just need to substitute variables. We're now going to substitute our known variable values straight into this formula, this transfer function here. So we end up with something that looks like this. However, by using MATLAB, this was easily calculated to turn out to be this transfer function here. Thanks for listening.